Okay, we have a derivative as a function, but if it's a function and we take derivatives of functions, then we could certainly take derivatives of derivatives, and in fact, it is useful. So, last topic in this introduction to derivatives as functions, what if we had f of x equals x squared? Well, then we know, because we computed it directly, that the derivative of that function is just 2x. But there's no reason we couldn't take the derivative of 2x and get this second derivative. Let's think about this for a second. If I was going to graph 2x, you could do this using the definition, but let's just graph it real quick. Here is my graph of 2x, a line with a slope of 2 right through the origin. And anywhere on that line, we've seen before, it should have the same tangent line. In fact, it is its own tangent line. So it should have the same slope everywhere. I know what that slope is. It is 2, right? The tangent line at any point is going to be the line itself. The slope of the line itself is 2, so that second derivative is 2. All right, well, we did it twice. Why not go again? Our third order derivative, we just do 3 prime signs. Oftentimes we get kind of lazy or it's just hard to look at, so we will instead do this parentheses 3. That is another notation. The derivative of 2. It's a constant, so maybe you know what this is. Maybe you could think about what that looks like. What should this be? Well, I'm going to do a quick sketch. That's what I often do. Here's my sketch of y equals 2. Okay, if I was going to do a tangent line, or even just think about how quickly that is changing, again, it's a line, but the slope of that line, it's just the line itself. Any constant function isn't changing. So the instantaneous rate of change, or the slope of a tangent line, it's just going to be 0. We see this kind of pattern of it getting simpler, these polynomials getting simpler as you take derivatives. So you get down to a constant, and then you get down to 0, and f, the fourth derivative of x, is just going to be the derivative of 0. But again, that is just a horizontal line, and I get a 0 out. Once you're at 0, you stay at 0. You can keep taking all the derivatives that you want. So no reason why we can't keep taking derivatives, and in fact, it's useful. There is another notation for this, which I'm going to introduce to you ever so quickly. We saw that if I want to take change my colors here. If I want to take the derivative of f, I could write this as df dx, or if I wanted to, dy dx. If I wanted to take the second derivative, I could take that derivative of df dx. This looks a little funky. The notation for this is d squared f over dx squared. And that squared is really over the whole, it's really over all of this, but we rarely write that notation. We rarely write the parentheses. So this would be d squared y over dx squared for a second derivative. This is usually a little weird the first time you see it, but it's good to know that you can write it this way. And we can write the third derivative as d cubed y over dx cubed. It's just like we're applying this dx operator 3 times to y. And this would be d to the 4th y over dx to the 4th. Sorry, a little bit sloppy on my writing there. Okay, cool. That's not going to come up that much, especially for these higher ones. But reading and writing derivatives is important. All right, let's see the most common classic example of this, which is in physics or engineering. So we've already seen this. If we have a position function, if I give you a time, you can tell me the position with this s of t. Okay, so if my position is s of t, then the derivative of position, okay, how fast is my position changing? That is just velocity. Okay, it is the instantaneous rate of change of position with respect to time. Okay, Now, if I ask myself, how quick is my velocity changing? How quick my velocity is changing, that's like if I was in a car, like this beautiful car here, if I slammed on the brakes or I put my foot on the gas, you're changing how quickly you're moving. That is called acceleration. Okay, so S double prime is also known as V. Oh my gosh. Sorry, friends. I don't know why I wrote velocity twice. Okay. And acceleration, we normally just write it as A of t. But it's the second derivative of position. Now, if you want some brownie points to show off that you know something that almost no one knows, there is a third derivative of position. And it has a name. So that third derivative is clearly going to be the second derivative of velocity, which is also going to be the derivative of acceleration. So how quickly is your acceleration changing has a name. It's a nice, funny one. It's easy to remember. It's called jerk. Okay. So I promise never to test you on jerk, but that's what it's called if you wanted to know. There's a reason for this. If we imagine that I'm in this car moving around, vroom, 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 vroom. If I'm going at a constant speed, that means I have a fixed velocity, but my acceleration is 0. Okay, and that feels like nothing really at all, right? You don't feel anything. However, if I am accelerating, say I start at 0 and I hit the gas and I'm going faster, 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 if my acceleration is constant, you feel a constant pull backwards, right? Gravity is a constant acceleration, and so you feel a constant pull down. If, however, your acceleration was changing, like you were on a train and you're jumping tracks or you're kind of going all over the place, what you feel is instead of that constant pressure of acceleration, that pressure is changing all the time and you feel like you're being jerked around. This is why it's called jerk. When you start hitting bumps and things and your acceleration is changing quickly, you feel that jerk. Okay, so just so you know, really common setup to talk about higher order derivatives. Notice that each one of these was with respect to time. You get really different things if you take derivatives with respect to different variables, right? There's no reason why I can't start taking derivatives of position with respect to, say, energy, or the derivative of area with respect to circumference for a circle. Things like this can give you really different looking examples, but this one's great for intuition. All right, that is it. Think lots, think deeply. I will see you next time.